Hi guys, welcome to Learn Electronics Repair. I have a ATX Power Supply here, as you can see. So this is one that I actually repaired on a previous video, maybe a year or so ago. And it's been in one of the computers at the workshop here, fine, working perfectly well. This computer doesn't get used all the time. It's really a backup machine. So most of the time it's just sitting there on standby. Every day that I'm working, the power gets switched off at night and it doesn't really do a lot of work. So this was sitting on standby. You can see it's a 600 watt supply. It's quite a hefty one, physically one, so it probably can't supply that. So this was sitting as it does on standby on the day before Christmas Eve, when all was quiet around the house, not a sound, not even a mouse, but there was a sound. So Detlef and myself were chatting about Christmas and stuff, of course, and all of a sudden there was a loud, that sort of noise, like a crack, and we kind of like jumped and said, what on earth was that? So no power had tripped off anywhere in the workshop, but there were so many things here plugged in, switched on or switched off, but connected to the mains, a lot of them switched off, but they may have some standby voltage in them, I guess, and we didn't know what it was. So we went around and said, well, everything seems to be on that's supposed to be on, and we tried the computers we use on the live streams, they powered up. So I came to this computer and tried to boot it up and it wouldn't start. So of course I put it on the bench, and the first thing I noticed is this power supply was really warm, but the machine had been in standby. It wasn't being used, but there was a lot of heat somewhere coming from this machine. I think it was in the power supply. It was really warm. So later that day I then took a spare power supply, put it in the machine, and the machine's working fine. Okay, the machine's now working fine. So I tested the power supply, attached it to my ATX analyzer, and it doesn't do anything. It doesn't go bang anymore. It doesn't trip out the power. In fact, it didn't trip the power. It didn't even blow the fuse in the cable to the PC when it made the loud. That wasn't loud enough. More like that noise. Okay. So it appears just to be dead. No standby, no nothing. So of course, I'm sure you'd be interested to know what went bang. What went bang in this? So let's get apart a little bit more than it is already, and then let's have a look to see if we can figure out what's happened to it, and maybe even resurrect it. So this is the power supply PCB. This is the PFC. This is the power factor correction. So this sort of sits behind the thing. This effectively is a voltage booster. So this takes the rectified mains, the rectifier down here, you can see the bridge rectifier, and it boosts the voltage up on the main capacitors from about 320, which is what you would normally get, to about 380 to 400. And this improves the efficiency of the power supply. That's the main thing it does. It will probably work without this, it just won't work at its full efficiency. This little PCB is still attached to the fan. This has this interesting cable which connects into this as well. And from what I can determine, this allows you to control the internal fan speed on the ATX power supply from your motherboard. Okay. So you connect this to like a chassis fan connector, and then the BIOS, you can control this like controlling any chassis fan. So that's what that is. This wasn't connected on my PC, by the way. If we get this little PCB off, we can probably disconnect this fan and then we can work on this more readily. So let's have a look, okay? This kind of like just sort of sits on top of here in a rather strange manner. Okay. And this is attached to our RC now, so we can unplug the fan. So let's do that. Okay. It's still not out of our way, so we have to unsolder this black wire, which you can probably see has been worked on before. And you see where I had to desolder this last time. So we'll just do that. when you're doing this sort of thing, I find it quite useful to just get a bit of braid and clear the hole, so it makes it easier to see where you've desoldered stuff from, basically. Of course, I've desoldered 2 holes, but they are connected together anyway, so that doesn't really matter. Right, so what happened to our power supply? What can cause it to make a loud noise like that and fail? I will say there was no smell. It wasn't like that smell you get from something electrical burning or from a capacitor when it's exploded. There was none of that acrid smell, so it just made a noise. I'm just going to make a quick visual check on this to see if I can see anything that's exploded, because it did make quite a loud noise. Okay, so let's have a bit of a look around. Nothing obvious there. How about this main board? Well, there's nothing burnt, but I say we didn't get any smell of burning at all. Okay, don't see anything particularly obvious there to look at. How about the other side? Can we see anything that is banged? Well, this is the output end. These are all the output capacitors. But, as I mentioned, it was in standby, so there wouldn't have been any voltage in here. Okay, controller, transistors. This is the standby supply. So, I can see down here, looks like a transistor or a MOSFET. And I can see 2 larger ones. So I think we can say that these 2 are driving the main transformer, and this one is the standby supply. So this stuff would have been powered up. But again, I don't see anything obvious. Okay, so let's make a few component checks, and if we can't find any obvious fault, let's try power this up and see what happens. So the power comes in here. This is the power coming in. This is effectively a fuse, so let's check the fuse first. As I mentioned, it didn't blow the fuse in the lead, and it hasn't blown the fuse here either, so the fuse hasn't blown. So it's not like we've got a short exactly on this, or at least not on the input. There could be a short further down in the circuitry, of course. So I think the next place we'll check for shorts is across these capacitors. Let's have a look. Well, you see where I've been working on this before, plus and minus marked on the bridge rectifier. Okay, so, well, we'll check for a short here, but I don't expect to find one because the fuse hasn't blown. No short there. AC, let's go to diode mode. As you see, I tend to drift around a bit when I'm doing this from one thing to another as the mood takes me. Looks good, and then to the negative, all the way round polarity. Looks good. That then goes into the PFC on the brown wire and back out on the red wire, and the red wire is a boosted voltage, and that comes to these capacitors, which I don't expect to find any problem. Okay, so no short there. I'm sure if there was a short somewhere like this on the input circuitry, the fuse would blow. Just some charge in the capacitors. So that's not it. But bear in mind, this was only in standby when it went bang. Let's have a look at this PFC. So we have 2 MOSFETs here and another device down here. That'll be a diode. Okay, it's got 3 pins on it, but I'm fairly confident that is a diode. In fact, if we look at it, yeah, the 2 outer pins are connecting together. Okay, you can see these have been unsoldered before. I mentioned I did repair this previously. I'll actually draw this part of the circuit for you just basically before we test stuff, because otherwise you may not follow what I'm trying to test here. So let's just do that. So the PFC circuit, I've described this several times in detail previously, so we'll just do this quickly this time. So what we have here is we have the AC, live, neutral coming in. This is where the fuse will be, or at least where it should be. And then we'll have a thermistor. I know because I've actually spotted it while I was just looking around. This is an NTC. So as this warms up, the resistance decreases. Okay. And this will come in. They could be in a slightly different order where these components are, but usually a filter capacitor. What may look like a transformer, but the 2 inductors may just look like an inductor. We'll look for it in a minute. And then we'll have another filter capacitor probably. I mean, this will vary a bit from power supply to power supply. And this will go into the bridge rectifier. AC, AC, plus and minus. So this turns the AC into DC. You'll now get this PFC, or power factor correction. Okay. So this involves basically an inductor, a MOSFET connecting to here, pulse width modulator, the PFC controller, a diode, and then we have our 2 large smoothing capacitors in series. Okay, and then this is the HT positive, the power supply to your switch mode, the main power supply. Okay. The way this works, by the way, is this MOSFET switches on and off at high frequency. And each time it switches off, you get a voltage spike coming out of the inductor, what's called back EMF. And this diode rectifies that. This will be a fast diode. Usually, in fact, I'd say always will be a Schottky diode. So we'll put the symbol here for a Schottky diode. And this rectifies these spikes and increases the voltage in the capacitor. So when this is not running, if you look, you just have your positive at your bridge rectifier going through a coil, which when this is not running, just a piece of wire through a diode to the capacitors. So without this running, you get about 320 volts DC here. If this is a 220 volts, 240 volt supply. When this starts running, the switching rectifies these high voltage spikes and charges the capacitor. The voltage here will then go to about 380 to 400 volts, somewhere in that region. Okay, so that's what this actually does. Now, a very basic test for this, we can't see any short circuits. We've checked here, we've checked here. I'll check this diode is okay. And we may as well check the MOSFET. But if there's going to be shorts in here somewhere, the fuse would blow. Or that would blow. But if that blows, you'd expect it to explode. Okay, so we can check to make sure this isn't open circuit. And then if that isn't open, we can check to make sure this isn't open. If it was short, it would honestly blow the fuse. And we've already checked there's no short across here, so that's okay. We can check these MOSFETs, but again, if they were short, the fuse would blow. So we'll make the basic checks anyway, because you never know, you might find something that surprises you here. If you don't do it, it was the time you should have done it. And if that looks okay, we're going to power this up and we're going to measure the voltage here. And if we get about 320, we know all the circuitry is okay, but the PFC isn't running. If we get 380 to 400, we know the PFC is running. So let's do it. Here's the PFC board then, and we can see, as I showed you before, this has two MOSFETs. These will be in parallel. So on my diagram, I actually drew one. I think what we're going to find here is we actually have a pair of these in parallel with each other, and both controlled by this, probably with their resistors. There'll probably be a gate resistor and another gate resistor there, okay, something like that. So that looks like what we have, two devices, but that's just semantics really. We can soon prove it anyway. The other thing on here is that diode I showed you in that circuit. So definitely nothing looks burnt on here, not visibly at least. Okay, so let's have a look. So the diode first. Well, the two outer pins are just connected to each other. You can see that on the PCB trace. Quite clearly, these two are just connected to each other. So from the outer pins to here, we should see a diode junction. And it's 0.402, so that's not a Schottky diode. This is what's called a fast silicon rectifier. So it's a kind of a cross between the two. It's faster than a normal silicon rectifier. You do need a fast diode in here all the way around. Yeah, it's just the capacitors are charging somewhere. It's gone to open now. And the same, we should be able to check the MOSFET. So we can see this end is the gate on both, and then we'll have drain source, okay, or source drain. I'm pretty sure this is drain source. I mentioned there was two and they look like they're in parallel. In fact, I think we can see straight away drain of this one goes to drain of this one, and looks like the source of that one goes to the source of this one. We can just check. So here to here, yeah, and here to here. So that's the gate here. So yeah, they are in parallel, and then I bet the gates will read like they're in parallel, but probably with a resistor. Yeah, see it says 0.34. If we go into the ohms range, gate to the gate, yeah, 44 ohms. So I think we can probably assume that there's two 22 ohm resistors, one going to each gate, and then the other end of the 22 ohm resistors are connected together on the pulse width modulator controller, and we're just reading through one resistor to the other. Yeah, so that's why we're reading 44. We could investigate, but you know what? 22 ohm resistors sound about right to me, so I'm happy enough. There's nothing mysterious there. Okay, so MOSFETs then, we pretty much know they're not sure, but we can test this. And we can also test which is the drain and which is the source. So if we put the red lead on the drain, so this would be the positive in the operation of the circuit. So red to positive and the black to the source. If we have them the right way round, you'd expect this to be open circuit. Something's just charging up a little bit, then it reads open. Okay. I'm a little bit surprised I saw something charging, but that's exactly what I did see. Okay. And the other way around, so this is the reverse direction with the negative meter lead to the positive. If these are MOSFETs and they're good, you'd expect to see a diode junction, and this is the drain if we do, because what we're going to see is the parasitic diode in each of these MOSFETs. Yeah. And of course it'll be the same on both because they're in parallel. So they look like good MOSFETs. The only thing a little bit strange, I didn't expect to see that something charging up there. The reason being that this would normally have, a very high voltage on there, and this would normally be effectively hot ground. Yeah, let's go on to resistance range. Well, I'm seeing about 12 meg, and that's kind of more like I'd expect to see. Okay, so we know the input circuitry is okay. We didn't check the NTC. This should be low resistance. Okay, if it's gone open, then the fault is a short further down. What does the NTC read? Get onto it. Yeah, 6.4 ohms. So that's reading low, and that's about what you would expect. So far then, I don't really see any problems with this. So the next thing is going to be, as I mentioned, power this up and measure the voltage across these capacitors. If we see about 320 volts DC, we know all this circuitry is okay, as much as there are no shorts or anything like that, or open circuits, but it means the PFC isn't running. However, you'd expect it not to be running when the thing's in standby. That's most likely what you would see, even if this is all good. If we see about 380 to 400, the PFC is running, but again, I'd be surprised in standby. Let's have a look. Okay, you can see I've worked on this before because I've marked it. So this is the positive end of the large capacitors here. I think we can just check on the capacitor. Yeah, this is the positive end. So we can say positive, negative, and then that's in series here, positive, negative. So if we go from here, this is the positive of one to here, which is the negative of the other. This is where we're expecting to see the 320 volts. Okay, I have the power supply connected via my current limiting light bulb. That's up there. It's set to current limit at the moment. You might notice, I'll just point this out to you. Okay, so I've just attached a little plug on here. Now this is a figure of 8, so you're going to say, well, there's no ground, and you are correct. There is no ground connected to this. Now my workbench is connected via a isolation transformer, mains isolation transformer. That means that on my main supply that's coming in on this particular connector, and by the way, any with blue switches in my workshop are isolated. But what this means is that there's no live or neutral here, only AC. So that means that if there's no ground on my workbench on this device under test, and it's not connected to anything else grounded like an oscilloscope, then I can physically touch live or neutral, and in either instance nothing will happen, nothing at first. Only if I happen to touch both at the same time, then I will get a shock. So that's why in actual fact there is no earth lead on this. Okay, your workbench may differ, so just bear that in mind or ask in the comments below about it. Okay, so let's have a look now to see what we have. We'll go to volts range. We'll watch the light bulb. Now when I switch this on, if the capacitors on here charge up, that should sort of flash once and then go out. So let's see what it actually does. Oh, you see it's flashing then flickering away. That looks like the PFC is running. That's what normally happens when you have an active PFC. Normally, if I see the light bulb pulsing like that, I just switch it out of circuit so I have a direct connection to the mains. I'm just going to have a quick look to see what we can see in these capacitors. Okay, so we'll just go back on again. Then that's the flickering. 270. So there's voltage getting into this, so it's not going to go bang or anything like that. But I'm a bit surprised to see that the PFC is running when it should be in standby. I've switched the power off, so let's have a look what voltage we have here now. 230, so it's holding quite a high voltage. You can see it dissipating. So there doesn't appear to be any problems on the high voltage side. Let's have a quick look to see if we see any short on the outputs, but bear in mind the only output that should be running is standby. which is the purple wire, which is just down here. So let's have a quick look. Resistance to ground. Okay, what we got? Well, it looks like we have a short. Yeah, it looks like we got a short on standby. Okay, so that possibly gives us some idea what's going on with this. I'll just let these capacitors discharge and then we can investigate that a little bit further. Okay, so we're down to 30 volts. That's about 15 in each capacitor. We can just discharge them anyway. Not that they're a hazard, but it helps when you're taking resistance measurements, for example. So this is just a little power resistor. I think it's about 2.7k, this one, something like that. And I can use this safely to discharge these capacitors. And 9 volts, 5. Let's just get rid of that. Close. Okay, so let's have a look. Just disconnected the main supply. So the standby voltage on this purple wire here, which kind of goes down here somewhere. Okay, you can see it there. Do we still see the short here? I'm guessing we do. Okay, so get onto that one. Ground. I think this is actually ground on this. Yeah, so we definitely have a short here. This will come through a diode, which is here. If we just zoom in a little bit. Okay. So we have 3 transformers here, which is normal for these sort of power supplies. This is the main voltage. This one's the standby voltage. That is your standby diode, which will charge one of, well, actually probably charges this capacitor. Then we have an inductor, then another capacitor, quite likely. We see the opto isolator here. The other transformer, that'll be driving the main switching transistors for the main supply. So the controller chip is here on the low voltage side. That will drive 2 transistors, be these 2, which drive this transformer, which then drives the main power supply. But our fault appears to be on the standby, which makes sense because this was in standby when it went bang. What can we see down here? I think this is just effectively old glue. We got this loud bang, but I don't see anything here that's actually blown up. There's another device here. This might be the TL431, the voltage reference, on the basis that it's somewhere very close to the opto isolator. In fact, we can see it says TL431, so that's in the feedback circuit with the opto isolator. So the best place to start is to remove this diode, I would think, and then see which side the short is that we're seeing. Okay, but bear in mind that the secondary on here will really affect you like a short anyway. There'll also be a second voltage output from this, and that voltage output will actually be powering these transistors, so, and probably this chip as well. So it may actually be that one of these capacitors, maybe that one, is on the other voltage output from here. Okay, let's get this diode out. So the diode is actually here. We can see one end goes to the winding on this transformer. This will read short anyway, whether it's short or not. I'll show you on paper in a minute. So that's reading short, okay? But it doesn't mean it is short, and the reason is this. we have the output of a transformer. The secondary, this is the standby supply. As I mentioned, this transformer will actually have 2 windings on it that will give 2 voltages. The standby is the 5 volts, this other one, auxiliary winding, is probably about 15, 20 volts, something like that, okay? But this is the one we're interested in. So we have a diode here. And then we have capacitor. This is safety ground, okay? We have an inductor. Or we might have inductor capacitor. We may even have 2 capacitors. We have something like that to smooth the voltage. And then this here is your 5 volts standby. Okay. So because we read a short circuit from here to here, there's 2 reasons why that can be. One is there actually is a short somewhere on this voltage rail to ground. So either one of these capacitors or whatever this is powering up is short to ground. But the other possibility is that there isn't a short there, but this diode is short to ground. So if the diode is short to ground, when we measure from here, we're just measuring the resistance of this winding to ground, which is practically 0. So just by measuring at this point doesn't actually tell us, have we got a short circuit diode and we're measuring that, or is the diode okay and we've got a short circuit somewhere on this voltage rail. This is why we need to remove or at least lift one leg of this diode. So let's do it. Okay, I've added a bit of flux. Need to get quite a bit of heat into this. More than I would have expected, but there we go. We've melted the solder now. Other end. I'll just try to desolder this with a bit of braid, or I may even be lucky to be able to kind of push it out of the board because it's a single-sided board. So we'll just push down on this end, wait till that solidifies, push down on that end a bit, wait till it solidifies. I think I've actually pushed that most of the way through now. Okay. Bit of braid. Okay. Yeah, that should come out, I think. I'll just get a little tool, something like this. I can just hook under that. No, find a better one. Yeah, something like that. Yeah, that should do the job nicely. Get hold of my diode. Sorry if you can't see this too well. And we'll just warm this and it should come out. Well, something happened. I think I just slipped off it actually. Okay, go again. Yeah, you see it's come out of that end. It's out. So here's our diode. This is not what went bang. We still haven't found what went bang yet, but I hope we will. What have we got? So we're on diode mode, okay. It's probably very hot still. Quite warm, but I can handle it. What do we have? We have a short circuit diode. So that's gone short, but is there another short? Okay. Well, once again, we'll go from the purple wire, which is down here, to ground. No, and the short's now gone. So it looks like that's what's failed. Now, it may be that because this has gone short, that the transistor, which is effectively driving this rail, which will be there, I would imagine, has gone or blown. That's that thing down there. Doesn't look visibly damaged, but it's a bit hard to see from this angle, to be honest. Okay. Must find my torch. It's actually at home, I know where it is. So, I think what we can do now is see if we can replace this diode. We'll power this up again with the light bulb on. So have I got something suitable for this? SB, that's a silicon barrier diode. This is a fast switching diode. SB540. SB540. Let me see if I can find something like this. This is the data sheet. I'm looking at SB540. It's actually a Schottky barrier diode. I had that slightly wrong. I called it slightly wrong. I sort of knew what it was, just called it the wrong thing. So here we have it. 540 is a 40 volts at 5 amps. Okay. I've just had a look and I've got some of these SB560. They are pulls, they're not new, but that's 60 volt at 5 amps. So it's basically the same diode, just a higher voltage version. That will be absolutely fine. So let's see if we can get one of these to fit into the board. And I say fit into the board because that's the short circuit one. Okay, I knew that was a stupid place to put it. Okay. So that's the short circuit one. We can see the markings clearly, 540. I have two of these, which are 560. We'll just test one. But the length of the leg is not long enough to get it to reach down to there. So I think I'm going to have to extend this a little bit with a bit of thick wire, but there's plenty of room in the power supply. Let's just check these are okay. Yeah, that's a good one. 0.24, that's what you'd expect for a Schottky, somewhere in that region. That's another good one. And this one, no, that reads short. That is short. Okay, so I'll just have to probably extend one of these legs a little bit and then we'll fit this. And let's see if our power supply then works. I've bent the wire over. These are very stiff, so I actually held it with the pliers down here while I bent it, save damaging where it goes into the component. I've soldered, you can see there's a bit of wire just looped back on itself, but that will go through the hole in the PCB just nicely. Let's just check it's still okay. Yep, that reads fine. So we'll fit this and we'll see whether or not it solves the problem. So obviously we found one fault on this ATX power supply, but we still haven't found what went like that. Yeah, because it was quite loud. And it appears that there's another problem on this standby power supply. We clearly still don't have a 5 volt output, although now there isn't any short on the output side. So to keep this one not too long, we'll end this just for a moment here. You can all take a break until tomorrow and we'll have a part 2. In part 2, we'll investigate what's going on the primary side of the 5 volt standby supply and see if we can see where the fault is and see if we can see what went bang. Okay, so hope you enjoyed that for now. We'll carry on tomorrow. I look forward to seeing you all then. Thanks for watching. Ciao for now, guys.